The diagram shows a uniform rectangular lamina ABCD of mass 5m. A particle of mass 2m is attached to B and a particle of mass 3m to C. Find the distance from AB and AD of the center of mass of the lamina complete with its load. So we can see we have a uniform rectangular lamina ABCD, okay, of mass 5m, and a particle of mass 2m and 3m is attached to B and C, and the side AB equals CD equals twice A. We can see it from the diagram, and the side BC equals AD equals 4A, and we are asked to find the distance from AB and AD of the center of mass of the lamina complete with its load. We can see AB is lying on the x-axis, okay, and AD is lying on the y-axis. So we are asked to find the coordinate of center of mass from x and y-axis by considering all the mass attached to the uniform lamina ABCD. Now, okay, we have uniform rectangular lamina ABCD, okay. So for uniform rectangular lamina, so for this uniform rectangular lamina, we first find or locate the axis of symmetry. Now, let us come back to this diagram, okay? So the length AB is twice A. So this is the midpoint, okay? So I'm taking it roughly. This is the midpoint of AB. And let's take this as a midpoint of AB. Clear? So if I divide this rectangular, okay, through this line, okay, then we get two equal parts. So this represent, okay, this dotted line represent one of the axis of symmetry. Axis of symmetry. In same way, okay. So I'm taking this as the midpoint of BC. Okay. So this is the midpoint of BC. And this is the midpoint of AD. Okay. So let us draw a horizontal line, okay, passing through these 2 points. So this dotted line, okay, represent another axis of symmetry. So this also represent, okay, axis of symmetry. Here, now what we find, the axis of symmetry meet or intersect at this point. So we need to note this, okay. So we solve this numerical problem by considering, okay, first by considering without loads. Clear? That is without mass twice m and 3m. Okay, so I'm redrawing this diagram. Okay, so we have this. This is x, this is y, This is A, this is B, or let me draw in this way. Okay, this is A, this is B, this is C, this is D, and this is the midpoint. Okay, and this is the midpoint of AD. So we have this. So this distance is A, okay, and this distance is twice A. Clear? And what we know, okay, from this diagram is that the axis of symmetry, okay, the axis of symmetry intersect at this point. So this is the point of intersection of axis of symmetry, okay, without load attached. So we have this case. So this point represent, okay, the point of intersection of the axis of symmetry without load. So represent, this point represent the position of center of mass without load attached. So this point represent the center of mass. So what we find, the whole mass of this rectangular lamina is supposed to be concentrated at this point, and the coordinate of this point is, we can see, we need to move a distance along x-axis and we need to move to a distance along y-axis. So the coordinate of center of mass of uniform rectangular lamina ABCD without load is A comma twice A. Therefore, okay, we can draw this diagram, okay, over here and this way. This is X, this is Y. So we have this, okay, this is A, this is B, this is C, this is D, this is without load, okay. So what we find, axis of symmetry is intersecting at this point, okay. So this point represents center of mass. So whole mass of this uniform rectangular lamina ABCD, okay, is at this point. So this is the center of mass. So we have this, and its coordinate is A comma 2A. So we have this. Clear? So this is without load. So this is to be noted, okay? Now next, we consider with load or particle of mass twice m and 3m attached to the rectangular lamina at B and C. So we have this, okay? Now, so this is the diagram, okay? Case 2. With load 2m and 3m attached. Okay, so we are considering this. So what we have, when we have this condition, okay, it means that we need to take rectangular lamina. We are taking this rectangular lamina plus particle or load of mass 2m and 3m. So we have this. Okay, we are considering both the load attached to the rectangular lamina. So we have to consider rectangular lamina, okay, without load, and rectangular lamina with load attached, because we are attaching twice m and 3m on the uniform rectangular lamina. So we need to take rectangular lamina plus the load attached. So we have this. Now we have found center of mass of rectangular lamina without load, okay, and its coordinate is a comma twice a. Okay, so we have this. This is a comma twice a, and whole mass of rectangular lamina without load is at this point, and the mass of rectangular lamina without load is 5m. So we have this. Clear? Now what we do? We are considering all the load attached. Clear? So what we do is that now we use the relation, okay? Since we have x and y, okay, axis, so we use this relation, summation mn xn equals x bar. This is the x coordinate of center of mass times summation mn, and for y, okay, coordinate we write in this way, summation mn yn equals y bar, which is y coordinate of the center of mass, okay, times summation mn. See, we are asked to find the distance from AB, that is distance from x-axis, and AD, that is distance from y-axis, of the center of mass of lamina with load attached. Clear? So we use these two relation. Okay, so we use these two relation. So this is x bar, okay, where is the coordinate, okay, of center of mass of lamina with loads attached. So we have this. Okay, so we have this. Now what we do? What we find is that, okay, using this equation, okay, so I'm taking this, taking summation mn xn equals x bar summation mn. Okay, so we have this. Now, as I said earlier, we have rectangular lamina, okay, along with particle of mass twice m and thrice m. So we have altogether three masses, okay. So we have three masses: 1 5m, 2 twice m, 3 thrice m. So we have this, okay, and its coordinate, okay, its coordinate is a comma twice a, and its coordinate, okay, we can see twice m is lying completely on x-axis, so its coordinate is, this distance is twice a, okay, so this is twice a, and its coordinate, y coordinate is what? 0. So we have this. Now its coordinate, okay? Let's say its coordinate is, see, this distance is twice a, so twice a, and y coordinate of thrice m is 4a. So we have this. Clear? So we use these data, okay, in these two equations. Now, 5m, okay, times its x coordinate is a. So we have a plus, next for twice m, okay, twice m, and its x coordinate is twice a plus, okay. Now we have mass thrice m and its x coordinate is twice a. So this whole equals x bar, and we have summation m, and we need to add all these masses. So we have 5m plus 2m plus 3m. So let us simplify this expression, okay? So we have 5ma plus 4ma plus 6ma equals, see, this is 10m times x bar. So we have this. Now, x coordinate of center of mass equals, let us add this, okay? So we have 15 ma divided by 10 m. So let us simplify this. So we have 1.5 a. Okay? Therefore, the x coordinate of center of mass, okay, of the uniform lamina by considering all the mass attached is 1.5 a. So we have this. Okay, this, sorry. So we have this. Now, let us use this equation, okay? Let us use this equation. Taking summation mn yn equals y bar summation mn. So we have 5m, okay, mass 5m, and its y coordinate is twice a plus, for this mass, okay, 2m, and its y coordinate is 0 plus, we have mass thrice m and its y coordinate is 4a. This equals, so we know total mass is 10m. So I'm writing directly, okay, 10m times y bar. So we have this, or let me write in this way, okay. This whole equals 10m y bar. So I'm putting this in a box, okay. So we have this. Now let us simplify this expression, okay. So we have 10ma plus 12ma equals 10m y bar. Therefore, we can write y coordinate of center of mass of the uniform lamina, okay, by considering all the masses equals, so we have 22ma divided by 10m. So this cancels out. Therefore, the y coordinate of center of mass is 2.2a. So the coordinate, okay, the coordinate of center of mass by considering the load, okay, of lamina, okay, is, we have this, okay, 1.5 a comma 2.2 a. So we have this. Now we can see we are asked to find the distance from AB. So we need to find the distance from AB, okay? So, and we need to find the distance from AD of the center of mass. So we have this. So this is the distance, okay? So we have this. So we can see from this diagram, okay? So let me erase this. This is twice A, okay? AB is twice A. Now, this is the midpoint. Let us take this as the midpoint, okay? So 1.5. So this is A. This is A. So 1.5 lies somewhere over here, okay? Let's take this as 1.5. So this is 1.5, and so this is this whole distance. I'm taking it roughly, okay? Let's say this is this is 1.5A, okay? This is 1.5A, and so this is the x coordinate, okay, of center of mass. Clear? So we need to find this, and the y coordinate is 2.2A. So let us take this as roughly, I'm taking this as the midpoint of AD, okay? So this distance is twice A. So 2.2A. So roughly I'm taking over here, okay? This distance, this whole distance, okay? So I'm erasing this. This distance, okay? Whole distance is 2.2A. Okay? So the center of mass of this uniform lamina, by considering all the loads attached, is at this point. So this is at coordinate 1.5A comma 2.2A. So we have this. Okay, this is to be noted. Now, what we do is that we put all these data obtained in a table, or let us tabulate all the data, okay, obtained. Load twice m and 3m attached to the rectangular lamina ABCD. The mass 5m is at its center of mass, and the coordinate of the center of mass is A comma twice A. Okay, so this is without load, okay, and the coordinate of mass twice m is 2A comma 0, and the coordinate of mass 3m or thrice m is 2A comma 4A. So we have this. Now we have three different masses, 5m, 2m, and 3m. Okay, so I'm writing in this way. We have portion AB, CD, okay, that is without load, and mass of this portion ABCD or mass of lamina ABCD is 5m and is at its center of mass. So next we have load at B. Clear? And next we have load at C. So when we add all these, then we get, okay, so let's look into this, okay, question. So we get complete lamina, okay, which is loaded. So what do we get? We get loaded lamina. So we have this, okay, and mass of ABCD without load is 5m and mass attached at B is twice m and mass attached at C is thrice m and the total mass, okay, is 10m. So we have this, okay. We can see this from the calculation also, okay. See, the total mass summation mn, okay, is this. And this is 10m, okay. So we have this. Now, the x coordinate of mass 5m is A and its y coordinate is twice A, okay. Let's multiply mass 5m with x. So we have 5m times A and let's multiply 5m mass 5m with twice A, okay, that is y coordinate. So we have 5m times twice A. We can write after simplification also directly in this way, 10ma, okay. So I'm writing in this way. And for twice m, x coordinate is twice A, y coordinate is 0. So mx gives me 2m times twice A and my is 0. Okay, so we have this. Now for mass thrice m, okay, or 3m, x coordinate is twice A and y coordinate is 4A. Clear? Now let's multiply 3m with twice A, that is x coordinate. So we have this 3m times twice A. Now let's multiply 3m with its y coordinate. So we have 3m times 4A. So this gives me the x coordinate, okay, of center of mass, and this, okay, gives me the y coordinate of center of mass, okay, and this, okay, give me, so when you look into this calculation, okay, summation mn xn equals x bar summation mn, and x bar summation mn is this, okay, 10m times x bar. So we have this, okay. So this gives me 10m times x bar, and this gives me, okay, when you look into this calculation, we have 10m times y bar, okay, we have this. This gives me 10m times y bar.